This podcast is brought to you by LMU Munich.
Thanks. Thanks everybody for coming. Thanks for PyCon Web and PyMunich for having me. It's almost noon. I know there's a talk after mine, but I don't want to keep anybody of you waiting for lunch, so let's get right into this. I'm Markus Holtermann. I'm a Django core developer since 2015. I'm working as a software engineer at LaterPay for a Munich-based company, but in Berlin, where we do micropayment for digital content. And today I want to talk to you about database indexes, but not necessarily when you want to put them or where you want to put them and how you get them there, but more so how they work, so you get an idea of how that would affect your web application. And in order to explain how database indexes work, I need to give you a bit of background theory in databases or in database theory. And well, as with most web application or most applications these days anyway, we have a lot of data we need to store, and we store that information most likely in databases, in whatever way. Django, for example, supports all kinds of different relational databases or SQL databases, and so I'm going to focus on those, given this is a somewhat Django-related talk. And because databases are such a huge topic, please don't expect me to tell you everything about databases and everything about indexes, because that makes for a hell of a talk or a hell of a conference. So this is a tiny part, tiny fraction of what's out there. What I want to tell you about today is how a database lookup works. Like the most fundamental, most basic things from which you then can start and derive how more advanced queries or more advanced things go. And I want to do this using a small example. Let's say we have this table in our database of people names with a primary key or an ID on the left and the age, for example, when they started coding. And now the task being at hand, I want to know the person or the persons that started coding at age 19. So the most obvious way to do that would be to, well, look through all the records in your database table, go from the first one, check if the condition applies, use that, or return this row. If it does not, go to the next row. And this query that we have there, you can express with like select star from people where age equals 19, or in the Django world, people.objects.filter age equals 19. And yeah, I said the straightforward way to figure out which records in the database table match is to go one record by record through this database table and return that particular row in this case, or the particular rows that match, essentially. And because we don't know how big the database table is, well, in this case it's 7 items, we are finished rather quickly. But now let's think about your project you have. There's not just 7 items in the database table. There's like hopefully 100 million, 100 billion, or even more. Like going through 100 million rows can take some time if you think about that. There's a lot of data your database needs to read. And going through these records one by one is essentially called a full table scan. And by full table, you can already picture it goes through a full table, which, as I said, takes some time. And what we want to do with database indexes, essentially, is to speed up this process of looking up all the records that match our condition we had before. I want to be able to, in a fraction of a second, with as little steps as possible, figure out which records match my query. And yeah, this is where database indexes join the party. Let's think about, or let me explain to you what database indexes are and how they work. And in databases that are used these days, focusing on relational databases, SQL databases, essentially, the most common database index type are so-called B trees or B plus trees. Their name comes from either the inventor or one of the inventors called Rudolf Bayer, or because they have a certain property which is called self-balancing, which for increasing amount of data gives you certain properties on this index that other types of indexes might not have. And this property is that you can get a guaranteed timing for whatever item you look up in this database. So if you have 100,000 rows, for each separate thing you look up, you have the same timing constraints. If you have 100 billion rows in the same table, well, the lookup is going to take longer, but it's going to take equally longer for every single item. So it's still something where you have a deterministic behavior independently of what you look up there. And this is a key component or a key aspect in indexes these days, because you can have, like, at least to some degree, have a guarantee on how long your database query is going to take. And to understand how such a B tree works, let me explain that given the example I had before. Pretty much as with every tree, both in computer science and in nature, we have a root. The major difference in computer science and in nature is that we put the root at the top and not the bottom, but well, so be it. This root node you see here consists of two parts. Well, 7, but 2 parts. You have the 3 nodes or the 3 boxes at the top, which in this case indicates that this root index node is of grade 3. And grade 3 means that this node can take 3 keys, and the keys are essentially the things you want to look up in your database table. So that would be a value from the H column we had in our database table. The 4 boxes underneath, they refer to either a different node in the index or to a row in your database table. And you will see how this looks like on this slide and the following slides. Let's put in the H11 and 37 at the top, because they were part of the database table. They were inserted, for example, first, and, well, they are just there. And now what this gives us is that whenever we look up a person with an age that is lower than 11, we look at another box, another node that hopefully has more information. If it's between 11 but smaller than 37, we look at this box. If it's greater than 37, we go over here. And if we have even more data, we potentially have another pointer from here to a 4th box. And, well, this thing can grow, and this is supposed to grow. But when it grows equally on every single level. Now, taking the values from the H column we had before and putting them into this index, we could end up with this. We have H3 and 5 in the leftmost node on the bottom, 11, 13, and 19 in the middle one, and 37 and 41 in the right. Now, what does it give us? What do we gain from that? Well, this is what essentially the index does. It provides some kind of a index. Instead of a full table scan, it gives a random access to data in our database table. Because each of these nodes at the bottom is going to point to the corresponding row in the database table. You will see that in a second. But we still have like this 4th pointer here empty. This feels like a bit of waste of space. And yeah, in some degree it does, but it gives a different property and gives a further and more advanced feature to indexes, which if you think about just making this thing point to the next node, you could do a so-called index scan, which I'll also show in a second, where you can just go through the index nodes one by one and don't always need to go back up the index and down again. This is, again, the last row in the database index we just had. You see how like these pointers go through, like this first pointer points to the row with H3, or this one with 13 goes down here where the age is 13. Like, I hope I didn't mess up the errors there. But the thing here being that once you are at this bottom node of your index, you have direct access to this one record in your database table that you can look up, that you can use, that you are looking for. And when we think about our database query again that we had just before, I want to select the person or persons with the age of 19. What do you think how the index lookup is going to look like? Well, it's pretty straightforward from my perspective. You have this first node, you check where in this set of keys we have in this node does the 19 go. 19 is certainly not smaller than 11, but it's greater equal than 11 and smaller than 37. So let's take this middle pointer and go to this node. That's one step. And then there's a second step, or only a second step, because we have the 19 in here already. So we can go, well, this jump here, oh, there's a 19, and this points to this row. And in total, we have 2 steps, or 3 reads, if you read the entire row here, to figure out the person of age 19. And because there is no other item in this index with a 19, we know we're done. And when you think about putting a unique constraint on a database field, at least for Postgres, this is going to pretty much happen, well, this is pretty much the way this is going to work. When Postgres is going to insert a new item in the database table, and sees there's a unique constraint, it sees if it can insert, if there's another key in this index with that value. So let's say we have there a unique constraint on the age column. If you were to insert another person who started coding at age 19, we would see, oh, hang on, there's already a person that started at age 19. I can't do that. We can't insert that person right now in this table because it doesn't fit our criteria of not having a second person starting at that age, which would be unfortunate, but that's a different story. I briefly mentioned index scans, which is where these arrows or these pointers join or help. Let's say you want to select all the persons that started coding in some age range. For example, in the range from 5 to 13. What do you think how this works? Well, it starts quite similarly. We try to find the lower bound, which is 5, which is obviously smaller than 11, which points us to the left node, where we find this key. So we can return this item from the database table. But then we have this upper bound of 13, where we can go and, well, let's take the next item that's bigger than 5, which, well, following this pointer, it's 11. So we can return this item, and we can go further to the 13 here and return this item from the database table as well. And still, we only have 1, 2, 3, 4, 5 kind of operations where we read from our database table, which is still faster than a full table scan, where we still would have 7 requests to the table. Now, if you have an index scan on the other hand with say 3 to 37, you would end up with still 1, 2, 3 references within the tree, and then 1, 2, 3, 4, 5, 6 references to the database table, which would make up for 9 operations, or 9 things you would start counting, which was then obviously more work than doing a full table scan. And this is a part of where the query optimizer, where the database needs to figure out when does it make sense to use an index, and when is a full database scan maybe faster or maybe more appropriate to do. So all in all, what you can see here is indexes are awesome. And this being a Django-related talk, I probably should start speaking about that. So let's have indexes in Django. And, well, actually we already do. There's dbindex, which you might be familiar with, which essentially just does that for a database table column. There is, if you are going to want to put an index on more than one column, you can go with index together and put just name and age in there, for example. And of course, there's this thing called foreign key in one-to-one field. This is in the underlying database implementation is pretty much going the very same way. It still has an index where it can easily look up references to other tables in that sense. And last but not least, there's of course primary key, which you most of the time don't need, but if you want to have something else than an integer field as a primary key, this is how you get a primary key, like the ID column in the beginning of this table to be the primary key. Let's go back about a year and a half. In 2016, Mark Tamlin and I had ideas for indexes and having them in Django. And Mark came up with some proposals while he was working on Django Contract Postgres. And we wanted to get better support and more features, pretty much like make Django support all the indexes that are out there. There's just this one thing called time that neither of us really had. So this wasn't going to happen just by us doing that. But there's also the thing called Google Summer of Code, which Django or the Django Software Foundation was lucky to be accepted again in 2016. And we had a student there called Akshesh, who was mostly mentored by Tim Graham, Mark Tamlin, and myself, essentially building a more flexible index API into Django. And it doesn't sound like much, but the result of this is essentially this one class, Django DB models indexes.index. And it takes a list of fields, and it takes a name. This is the very basic API that Django 1.11 ships with. Now, how do you use that? Well, there's this thing called class meta on a model that now gained an indexes option, which is a list where you can put in an index for a field, give it a name, and this is essentially part of a new API. Granted, this is something you can do with dbindex equals true. So that doesn't bring us much. But then, well, we can also make asset fields being a list of field names. We can put 2 field names in there. And yeah, granted, again, this is something you can do with index together. So why the heck do we do that? Well, because of things like this. Gin index, for example. A gin index can be used to index the, let me get this wrong, can be indexed to use, a gin index can be used to index the key values inside a JSON blob. So if you have a JSON field in your model and want to look up some value in there, you don't want to go through all the JSON stuff, like unpack the JSON blobs and try to see if something matches or not. You want to have it performant. And having a B-tree on there doesn't really work, but having a gin index, which has, in the underlying, very basic underlying things, works similar to the B-tree index, but on the deep down implementation level is entirely different, so to say, gives you this possibility. And, well, this is kind of like the one-on-one in NoSQL. Another thing that was added to Django 1.11 as a special index, also Postgres specific, is the so-called Brin index, which gives you much better performance for certain types of aggregations. So if you want to count the sum of all sales per month, this is where you kind of go. And because indexes are part of the database schema, they are obviously tracked through migrations. So this is when you kind of what happens when you run migrations with indexes. Now, let me get down some feature ideas. Because this is what ships with 1.11. This is great. This gives us a whole new API that we can expand on and that we can use to add more things, more advanced, more fancy stuff in the future. What could we add there that is missing and you can't do with Django right now? And I think the major part there being so-called functional indexes. Let's say you want to look up by the lowercase version of a name, but in descending order. Why? Well, it doesn't really matter here, but let's say this is one of the conditions you have, or anything similar to that, or compute the sum of two columns, whatever. This is what you could do there. This is an API. I got most of the implementation down for Django 2.0. A couple of tests are missing. But yeah, this is something you will be able to do in Django 2.0. And this is a huge milestone in the support for indexes in Django. Because this is something you couldn't do before without writing raw SQL in migrations. Another thing I think that Mark is working on that is the dbindex, as we had that before, as I mentioned before. That doesn't really make sense for some for some data columns in your model. So maybe set a different index type there and let Django figure out the rest. Or for the JSON field, for example, just set a default index class that kind of correlates with this thing we talked about, that I just talked about before. And then, for whatever reason, there is no gist index in Postgres, in Django 1.11, which has some features for geospatial information, like give me all points that are within a distance of 10 of a given point. There's a ticket for that, which is 28.126. If you want to work on that, this is something I think really good to start with. And yeah, so there's a bunch of stuff Django 1.11 supports in terms of indexes. There's a bunch of stuff that we're going to see in 2.0. And yeah, I think I hope this talk gave you a bit of an overview of how indexes work in Django, or in databases, and then how you can use them, or more specific things in Django. And yeah, hope somebody of you might contribute to that issue. Thank you.
Okay, thank you very much. We have few minutes for questions, so anybody have a question? Yes, please.
Yeah, so we talked about database indexes, and now consider the following. I have a huge table with name and age, and now I want to speed up my query because I look up for the age in the table. When I apply an index to an existing table, is there a small danger? Is there some database processing in the background, or yeah?
So repeating the question, are there any drawbacks in creating an index on an existing table with potentially millions of rows? So it depends a bit on how exactly you create the index in your underlying database, of course. Postgres does have a thing called concurrent index building or delayed index building. So you essentially create the index, and then either Postgres, while creating the index, goes through all the records and potentially logs columns or does enforce certain locks on the database table. And there's the other one that essentially happens after you edit the index. It's going to do that in the background, so to say. So this is, I'm actually not sure what we currently do. We should probably check that and potentially add this as a separate option to how you want to create the index. But yeah, there's essentially, in Postgres at least, there are two options how you can do that.
Okay, there is no time left. Thank you very much, Markus.
Okay.
Thank you very much. And if you have any question, you can come to Markus, I
Yeah.
think, and ask him. The other thing, please, plastic bottles, don't throw them in garbage. Don't do it, because in Germany we utilize them. So just put it on the table, okay? That's all, and enjoy your break. Next speak is because web IP testing should be easy. 5 minutes.